Hello guys, so today we are going to present our assignment which is a solid group assignment. So we are from group 1 section 2 and this is our assignment presentation. So here is our group team which is me, Umar, and we have Khan Lamia, Nor, Babakarani and Abdul Halim.
A simple rehabilitation device may look harmless, but it still needs to withstand repeated user forces during the daily use. If the structure is not properly designed, it may deform or fail and affect the user safety. In this project, we use solid mechanics principles to analyze the safety and structural performance of an elbow crunch stick used in rehabilitation. The main goal of this project is to design a simplified elbow crunch stick and study how the changes in stick height affect its mechanical behavior. We aim to propose a safe and reliable design, gain hands-on experience using SolidWorks for modeling and simulation, and evaluate stress, strain, and deformation. The manual calculations are also done to validate the simulation results. Our analysis is based on the basic solid mechanics principles. Stress refers to the internal force within the stick. Strain describes how much the stick deforms, and deformation shows the overall change in shape or length. Hooke's law is used to make sure the material stays within the elastic range, meaning it can return to its original shape after use. In our design, the elbow crunch stick mainly experiences an axial stress, which we analyze to ensure it can safely support the applied load. For this project, we use SolidWorks 2025. The CAD module helped to create the accurate 3D models of the elbow crunch stick with different heights, while the simulation module was used to analyze the biomechanical properties under a user force. This allowed us to visualize the results clearly and confirm that the design is suitable for rehabilitation purposes.
In this project, we designed and analyzed a medical crutch using SolidWorks software. The main goal is to test the durability and stiffness of the crutch under loads to ensure user safety. We focused on the main part, the metal rod. We compared three different lengths: 800 mm, 850 mm, and 900 mm. To see how length affects performance, the material chosen is aluminum alloy because it's light and strong, with yield strength of 108 megapascal. To run the test, we used static analysis. We fixed the crutch from the bottom and applied a vertical axial force of 150 newtons on all three lengths. This simulation, the user weights leaning on the crutch. Based on the simulation reports, the results were excellent and showed the design is safe. First, stress. The results showed that the maximum stress ranged between only 2.16 megapascal and 4.37 megapascal. These values are very small and safe compared to this material. Second, displacement. The bending in the rod was very small. The results showed a maximum displacement of about 0.03 mm for shorter modules, reaching only 0.09 mm at the longest length. These numbers prove the crutch is suitable. Third, strain. The strain values were extremely low, with maximum ranging between 26.5 micro and 53.5 micro. This means the relative deformation in the crutch material is almost zero and does not affect its structure.
Presenting the manual calculation analysis for our elbow crunch stick design. We evaluated three different stick heights: 800mm, 850mm, and 900mm. As you can see from our free body diagrams, each design features a hollow circular shaft with an outer diameter of 25mm and an inner diameter of 23mm. We applied a consistent axial load of 150 newtons at point C, which results in a reaction force of 150 newtons at the base. This setup allows us to compare how length impacts the structural integrity of the stick under a standard user load. Moving on to the internal forces, our axial force diagram shows a constant compressive force of negative 150 newtons throughout the shaft. To find the normal stress, we first calculated the cross-sectional area using the hollow circle formula. With an area of 754 times 10 to the power of negative 5 meters square, we determined that the stick experiences a uniform compressive stress of 1.99 megapascals. Since the cross-section is uniform across all three height variants, this stress level remains identical for all designs. While the stress is constant, the deformation, or how much the stick physically compresses, changes with height. Using the axial deformation formula, delta is equal to PL over AE or FL over AE, we calculated the displacement for each case. As the height increases from 800mm to 900mm, we see a linear increase in deformation, starting at 0.023mm and reaching 0.026mm for the tallest stick. Although these values are very small, they are critical for understanding the material's elastic behavior. To conclude our analysis, we've identified the 900mm stick as the critical condition. While all three designs are safe, the 900mm version experiences the largest axial deformation and has the lowest buckling resistance due to its length. Therefore, if the 900mm design meets our stiffness and stability requirements, we can confidently say that the shorter versions are also structurally sound. This analysis ensures that our elbow crunch stick is optimized for both user safety and performance across all height adjustments. Beyond simple compression, we must ensure that stick doesn't buckle. We calculated the critical buckling load using Euler's formula. There is an inverse relationship here. As the stick gets longer, its resistance to buckling decreases. The 800mm stick can withstand 5,778 newtons. The 900mm stick capacity drops to 4,565 newtons. However, even for our tallest design, the critical load of 4,565 Newton is significantly higher than our actual load of 150 Newton. This gives us a very high factor of safety, confirming the stick is completely safe from buckling.
First, existing elbow crutches offer better mobility than auxiliary crutches, but long-term use still leads to high energy expenditure and significant loading on the upper limbs. This often causes fatigue and discomfort at the hands, wrists, and forearms. These repeated loads can result in reduced walking efficiency and over time contribute to repetitive motion injuries, which shows that current designs are not fully optimized biomechanically. For this project, a simplified hollow tubular model was chosen to focus on the primary axial load path. This allowed us to perform clear manual stress and deformation calculations and also directly validate them using simulation. Our proposed design ensures uniform stress distribution and efficient load transfer. Under a 150 Newton load, this crutch shows minimal deformation and a very low stress for all three heights. Finally, the high factor of safety and buckling analysis confirmed that the design is structurally safe, stable, and suitable for adjustable use without compromising user safety.
So here come our conclusion. Since that our analysis confirmed that the elbow crutch design is structural sound with simulation and manual calculation showing total agreement on safety limits. Although the 900mm model show the highest displacement, all designs stay within safe stress levels. Further, Future interaction will expand beyond static axial loading to include more complex real-world movement. That's all from us. Thank you.